Screen share? No, it's not
No,
required.
Later.
later.
Okay.
Yeah. Okay, ready. Amish sir.
So, yes. Good evening to one and all present here. I, Dr. Amrish Badgujar, Head School of Engineering Technology, welcome all the participants to this joint seminar series organized by Navratna University and Thomas J. Watson College of Engineering, Binghamton University, New York. Today is the first talk of this session, and in this series of a joint webinar series. And on this occasion, I request Provost Navratna University, Dr. Nilay Yagnik, to share about this particular collaboration and about Navratna University.
Thank you, Dr. Amrish. On behalf of Navratna University, I welcome all participants who are attending the very first webinar today, joint webinar of Navratna University and the Thomas J. Watson School of Engineering and Applied Science, Binghamton University, United States. We have with us a very distinguished gentleman, Professor Michael Testani from the State University of New York, Thomas J. Watson School of Engineering, Binghamton. And he is in charge of outreach for the entire university. And he brings with him several decades of experience in both academia as well as industry. The collaboration that we have with Binghamton is a result of several months of discussions which I have had with the Dean of the Thomas J. Watson School of Engineering, Dr. Srihari Krishnaswamy. And I'm so grateful and so thankful to Dean Srihari Krishnaswamy and the entire Thomas J. Watson School, Binghamton, for agreeing to collaborate with us. The idea is to exchange ideas as well as to exchange research projects. We are starting off initially primarily with a joint webinar series. You must have seen the calendar from April to July. And the model we are following is that first, today's webinar by Dr. Kedar Pathak. Dr. Kedar is a faculty at Navratna University. And the next session will be a faculty from Binghamton who is going to speak on autonomous systems. And then following that, there's another topic on where there's a faculty from Navratna University. So we are going to alternate up till July. Some very interesting and extremely relevant topics, cutting edge topics, will be discussed in these webinars. Once that is over, we will also be discussing joint research opportunities, faculty exchange, student exchange, and such kind of projects which will go on. So it's a long-term relationship that we have tied up, with Binghamton, and we are really looking forward to adding value, mutual value. And I'm looking forward to their visiting us, hopefully when the pandemic is over. I'm looking forward to the Binghamton people, Dean Srihari and Mr. Michael, coming over and visiting our campus in Vadodara and meeting our students in person. So thank you once again. Thank you to all the participants. Thanks to Professor Michael for joining us today. My special thanks to Dean Srihari Krishnaswamy and all faculty colleagues and students of Navratna University as well as Binghamton University. Thank you. And I look forward to today's lecture. Thank you.
Thank you, Provost.
Thank you, sir. Thank you, sir, for such a nice introduction. And I now invite Professor Michael Testani, Director Industrial Outreach of Thomas J. Watson College of Engineering, Binghamton University, New York, to say a few words about this collaboration and an overview of Thomas J. Watson College of Engineering, Binghamton University. Sir.
Well, thank you so much, Dr. Amrish, Provost Nilay, Dinesh, our esteemed speaker today, Dr. Kedar. I'm delighted to be here on behalf of Dean Srihari. I'm honored to be a part of this collaboration. as the provost has rightly pointed out, we are looking forward to a long-term collaboration here that will include all of the things that the provost had mentioned. And we're starting this with this technology exchange, right, where we're sharing research on leading topics that both of us are working on. And I think, both organizations are keenly interested in, because, these are the leading technologies that will shape our future, right? And we're beginning to see that now. So I'm really excited to be here. Delighted to be a part of this collaboration. I think it's a wonderful thing. I think it will only continue to grow over time and become more impactful. So thank you so much for having me, all the organizers, and certainly for all those students, faculty, and staff that are on the call. Thank you so much for joining, and we look forward to seeing you in future sessions for sure. So I just want to take a few moments just to overview the Thomas J. Watson College of Engineering and Applied Science. We're here at Binghamton University, and I just want to give you a sense of what we're all about, but I promise I won't take too much time away from Dr. Kedar, because that's who you're here to see, and I understand that. But in Watson, we're a world-class higher education institution. We are focused on high quality, high value learning in engineering and applied science. And we have a very, very strong international perspective. And it's that perspective that brings us all together today. And I couldn't be more delighted. I'll just briefly cover a few things about where we stand in terms of rankings, and really just some of the programs that we offer that I think would be of interest to students at your organization. And we'd love to see you all on our campus at some point in the future, that's for sure. But in terms of rankings, we do quite well. We continue to move up in the rankings. I won't read through all the list of rankings here. These are just a few, but a couple I thought you might be interested in. Kiplinger magazine, which is a very popular financial magazine, lists us as number 7 in terms of preferable colleges and universities for out-of-state and international students. So we're quite proud of that ranking. To be in the top 100 is great. Top 10 is excellent, and we're delighted to be number 7. Money Magazine, another financial publication, they have us number 9 as the best public university for ROI after graduation, and that's a very true statement. In fact, I think we're a lot better than that, because I know we're a tremendous value. We're part of what we call the SUNY system, right, which is the state universities of New York, which means we get some support from the state, which helps us keep tuition down. And I can also attest to the fact, since I keep in close contact with a lot of our alumni, they do extremely well post-graduation. I mean, I talk to folks that are, not only at director and senior director levels after, 10, 15 years after graduation, they're a vice president and, some even CEOs of their own companies. So we're really proud of that. And I would say, we're doing that because, for the students that come from India, we're really just standing on the shoulders of the preparation that's already been done. Right? Your technology programs are excellent, and we just build on that. So we love this relationship because everybody wins. We like being number 1 in terms of not only the best public college in all of New York, and there's probably hundreds of colleges across New York, in the entire Northeast. So that's several states in the northeastern part of the United States. We're the best public university. So we're quite proud of that. And as I say, we'd love to see you all here someday. And here's this U.S. News and World Report. This is considered the hallmark in terms of college rankings. And you can see where we rank here as public universities and overall. So, in the top 50 public, overall, well within the top 100. And we're continuing to climb, which we're proud of. In terms of the Watson College, we're not too big and we're not too small. So we think we're right sized. We're just over 3,000 students at our Watson College. So it's a good size. We'll grow a little bit more over the next few years, maybe up to, 4,000 students. And then we think we're right sized, and we continue to add faculty so we can keep that favorable student and faculty ratio. And I'll share with you in a bit some of the programs that we offer. So you can see quite a bit in terms of engineering and applied sciences. Engineering, certainly electrical, mechanical, industrial engineering we offer, but system science, systems engineering in healthcare, data analytics program, computer science, of course, and biomedical engineering is another program we're quite proud of, and offer certificate programs as well in cybersecurity, system science, and complex system science and engineering. So, those are the programs that we're quite proud of at the Watson College. We're quite proud of the fact that we've become more and more competitive over the years. So you can just see our SAT scores here, how they've grown, over the past 10 or 15 years. So we're proud of the fact that we bring in the best of the best students from around the world. And, we'd love to include you in that population as well. We do a lot of very significant research. We have, dozens of research centers. These are those in Watson. I think we've got 10 or 11 here listed on this slide. And the research ranges from, solar cell construction to small scale electronics packaging, to healthcare systems, bioengineering, cybersecurity. So a lot of research going on campus, and state-of-the-art labs. Our students really love the opportunity to, get involved with state-of-the-art equipment and gain some great experience as they're performing their research. A lot of job opportunities on campus as well. So this is what helps our students, pay for their living expenses. I mentioned our tuition being very attractive, but we also give our students, there's literally thousands of jobs on campus that our students can attain, and this helps them pay the rent, helps them pay for living expenses while they're experiencing the university experience. Another thing we're quite proud of is, since we've been around for decades, we've built up some strong relationships with industry. So you can see all the industry names. I'm sure you recognize many of them. In fact, I worked for 20 years prior to coming to the university a few years back. I worked for IBM for 20 years. So you see them on the list, as well as dozens of other well-known companies around the world. And what this means for students is internship opportunities while you're here on campus, and certainly a pathway to employment, right, if this is the pathway you choose. I mentioned how our alumni do quite well. Here's Haren, who's talking about his experience. And as you can see here from his quote, he's had a wonderful experience while he was on campus. He's now the director of product management for Qualcomm. So, he's doing quite well post-graduation, and in part is acknowledging the Watson College, for that. We're quite proud of our diversity. So our students come from over 50 countries around the world. So diversity, equity, inclusion is a core value, not only in our students, but also in our faculty. We want our campus to look like the entire world, right? And we're getting there. And finally, before I turn over the floor, I just wanted to acknowledge a recent achievement by the university, and particularly Dr. Stan Whittingham, who's recently won the Nobel Prize in Chemistry. He and his colleagues had developed the lithium-ion battery. So the battery that's being used to power your cell phones, your laptops, your tablets. We owe credit to Dr. Whittingham for that invention. So we're quite proud to have he in his lab and the research going on our campus in terms of energy storage. So thank you for allowing me to introduce our campus a little bit. We're proud of what we do. We're proud of this collaboration that's starting with you all. As the provost mentioned, this is the first in a series of 7 talks. You can see the various talks we've got scheduled through July. So we want to make this a really rich learning experience for you all. And I think you'll find that to be the case. So thank you. Thank you for joining. With that, I will stop sharing and we'll turn the floor back to Dr. Amarish.
Thank you, Professor Mike, and thank you for sharing that particular schedule. Now, it is my pleasure to introduce the first speaker of this series, Dr. Kedar Pathak. Dr. Kedar Pathak has been associated with Navratna University for last 5 years as an associate professor in mechanical engineering department. Dr. Kedar did his postdoctoral research at NASA, as we discussed, and he did his PhD from University of Akron, US. He did his master's, MTech, in aerospace engineering from IIT Bombay. Dr. Kedar Kedar's research area is thermal and fluid science engineering, and he has made a significant contribution in the field of computational fluid dynamics. Dr. Kedar has been associated with various projects with AICT and Department of Science and Technology, India, DST. And as of now, he is working with one of the projects sponsored by Defense Agency in India, that is DRDO. With this brief introduction, I would like to invite Dr. Kedar Pathak to present his talk on essentials of computational fluid dynamics. Dr. Kedar.
Thank you. Thank you very much, Dr. Amrish, Professor Nilay Yagnik, for initiating such a collaboration, Professor Mike, and I wish to prosper this collaboration, and it may help for both of us a win-win situation. So I'll begin with sharing. So I will be talking about computational fluid dynamics. Looking to the variety of the audience, I will just brief about the essential ideas of the computational fluid dynamics there. So with this aim in mind, this presentation is to see the major chronological developments of CFD, their cause, and what CFD is as it is today. And this we will do without any discussions, rigorous discussions on the equations there. So therefore, those who already having a background would be exposed to the challenges in this field, and those who do not have any background may would appreciate the perspective that the CFD took. So, well, CFD is wherever there is a flow. So in terms of applications, there is enormous applications for the CFD. But the crucial development of CFD, as we will see in this talk, came from the requirements of the aerospace industries. The commercial aircraft developments gave the thrust in the development of the CFD. Other applications of the CFD then subsequently added to this development are just to name few here. The car design, racing car, fast car designs, then gas turbine engine design, which is very crucial because this gas turbine runs at very high speed. Then internal pipe flows, external flows, energy conversion for power plants. There are advanced applications which includes biomedical applications, nanotube synthesis for a new material development. There also we use CFD to see the dynamics of the materials wherein the plume is formatted. And there are other enormous applications. So this is how the CFD. This is just to show you that it is also useful in various sports activities and so forth. So these are what you see, the streamlines of the flow past the bicyclist. So now this is a very good book. I would say I suggest this, wherein this quote tries to say that, having said all about this CFD, we see so many pictures, displayed in the glorious details. But what he's trying to say is, what about their accuracy? Do we understand the accuracy, the correctness of the result? And that is where the gist of the CFD is. And that only comes from understanding the basics of the fluids, or the basis of the aerodynamics. Well, in this talk, because I would like to give you the historical perspective as well. So this is the guidepost. This can remain as a guidepost of our talk, wherein this is roughly a Moore's law. On the y-axis, what you see is the millions of instructions per second, and how it grew over the last few years. So you see, these manufacturers value their computer manufacturing in terms of MIPS per dollar per cost. So, and this has steadily doubled, as you can see here, and we will see what, how it grew and what parameters it affected. So this is a roughly a Moore's law, where it says everything that is interesting about this computer doubled within 2 years, per 2 years. So it started, the journey started with a scientist named as Richardson. And you see, he started this in the era 1906, around 1906, when there was no computers. So how can we add this point in this graph? So that is what we will discuss here. So he was a mathematician. Richardson was a mathematician, and he was employed for various companies, wherein his first job was to drain water from a big marsh there. So, and it was a complicated task. So what he did is he employed a numerical method, and he was successful. Numerical method is simply, he just had the finite differences applied to a region of the marsh, and the calculation gave him the correct result based on the gradients that he observed. So this suggested to take on this method of discretization, and he took to calculate the stresses into the machinery dam. Now this was the big project in the 1906. You see, apart from this, I would like to mention, in this era around 1905, there was awakening of the quantum mechanics as well. You see, so it was the people were trying to resolve the things at a atomic level, and there were people, mathematicians, who were trying to deal with the macro level. So this Richardson was one of the pioneer who applied this field equations to the practical problems like this. And what he did, how he did is, you see, the dams were not perfectly rectangular or perfect shape, and that's why you need to do various computations. And in order to do, he employed a team of the students who were good at arithmetics and mathematics. So so this, what they did, the students' computations were the part of something which is bigger, and then he integrated this all the results together, and he was eventually able to compute the stresses. So that is how we could place the Richardson's in that MIPS per second graph. So now what he was doing is, he was essentially trying to solve these equations. Now these are called Navier-Stokes equations. They are full Navier-Stokes equations, and they are not solvable. It is one of the 7 problems. So his idea how to solve this equation, his idea, we'll see. His idea was to discretize the domain wherein you apply these equations, and then there is a gradient term in this equations. You see this dou by dou x, partial of x, and the second derivative of this. So based on the systematic approach, he came up with this weights on the given nodes, and this was based on the Taylor series approximation. So once you have a systematic approach, all you have to do is plug in these partial derivatives into those equations. So when you stuff these derivatives into those equations, which is a systematically derived equation, so they are perfectly arithmetic calculations. So this is the finite difference idea of the Richardson, pioneering idea of the Richardson. So this he wanted to, based on his successes in the previous calculations and deployment of the numerical methods, weather forecasting was his area of interest, wherein he wrote a book also, weather forecasting by numerical method. So during this era 1914, there was a World War One also, First World War, wherein you will be exempted only when you do certain voluntary services, wherein he chose to row the ambulance. So you see, he struggled a lot during this, you know. So, anyways, so because he was interested in those calculations, he had a data, let us say, for in the area of the Germany for a particular day, and this data he fed into those equations which we have seen with the numerical methods that we have seen, and nothing happened. His predictions were 100 miles per hour, but nothing happened in those days. So something went wrong. So here is the essential of the CFD comes in. So what went wrong is where we'll see now. So it's not only about numerical method. There is some physics also that is built into those equations. So we'll take an example of no, just this is the equation that you see. Temperature, variation of temperature with respect to time is governed by the second order derivative of temperature with respect to space with some constant here. Now, according to Richardson, what you do is you discretize these gradients on the left hand side and on the right hand side. So there are various ways in which you can do, but only one of them will work. So on the left hand side, you discretize the domain, the time derivative of the temperature using 3-point stencil, the x derivative using 3-point stencil, and this left hand side doesn't work, whereas the right hand side works. Now, in those times, because if Richardson would have done enough of the calculation, he would have seen the pattern. But no, there was no computer, so that was anyway. So why this doesn't work is because now there is a physics into this equation. The physics says that the heat can only flow forward in time. If you now this left hand side figure is backward in time. So any backward in time, this which does not account for the physics, and the beauty of the equation is they fail. There is instability into those equations. Now we will not go into those instability, but there is a beautiful connection of this simple arithmetic equation which will not work if you don't account for the physics. And if you account for the physics, this simple arithmetic would work. So that is the beauty of these equations. Another important event which developed the CFD is this Los Alamos project, wherein they wanted to evaluate the shock strength. Now, whenever there is an explosion, there is a shock wave which travels, and which is a very important feature of this explosion. So this is usually you compress uranium about its supercritical density, and the explosion follows. But what is important to calculate in this explosion is the shock strength, which is much ahead of the material which follows that shock. So in that also, Feynman was leading this project, Richard Feynman, and he employed again good students who were good at arithmetic and mathematics. They used to compute the different parts of the project, but this time they were very good at. So they realized that no, there is a trend wherein we can set in this calculation. So this is the first indication of the programming of the equations. So this suggested, and at this time there were the mechanical computers available to them. There was no electronic computers, so there were mechanical calculators available. But again, there is the same problem whenever you want to calculate the shock strength and the shock wave, you just do the discretization, you plug in those discretization, and then you don't get the correct answer. So this is what again, the shock wave has a different physics than the heat flow. So who this is John von Neumann, who was interested, who was a leading mathematician and who was interested in all those problems, and he would run to solve those problems. So Richmond and von Neumann um, got to the heart of the problem, which was which was the instability due to due to not taking care of this physics. Now the shock wave was very sensitive problem. So by tackling the shock wave, they realized that there is something called as viscosity, which if you artificially add to this numerical discretization, uh, because you see this shock wave involves thermodynamics also. There is an entropy generation, which is not taken care. So this artificial addition of the viscosity would allow for the entropy generation, which is irreversible process. So anyways, this von Neumann stability is very well known. So there is a method, systematic way, wherein he saw the instabilities and then he took care of those instabilities. So now having done that, they used this computer, which was the electronic numerical integrator. ENIAC computer was the first large computer, and surprisingly, this was built by physicists and mathematicians. So, and this computer was it did various calculations, and it helped to understand the pattern of these numerical uh, equations that we solve. So now this in this guidepost we can see that this ENIAC was built during 1945, 1947. So we are here, and from the here we see the trend of the Moore's law, where there is a it is a log plot, so this is a straight line, but it's doubling. These effects are doubling here. Another important development of the CFD is due to this Battle of Atlantic. People wanted to cross this ocean as fast as possible. And there were two companies, Boeing and Airbus. So they were fighting for that, and faster is what they wanted. Faster and higher is what they wanted. So what is stopping them from going faster is this drag rise. You see this in this picture. If you travel faster than around 0.8 Mach, 0.8 Mach is we are very close to the speed of sound. So if you somehow are close to 0.8 Mach, then suddenly your fuel consumption goes very, very high. So now the problem is, where should we fly? At what point in this graph we should fly? Obviously, the point is where we just deflect around 1.2. But then how to do this? The problem with the wind tunnel testing here is, as you are in the region of the supersonic velocities, there is something called as vortex stretching, and these vortexes will travel span-wise, and if there is a wind tunnel, it will hit the wind tunnel wall and come back, and then no testing can give you the correct result. So people turned towards the theoretical computations, and Euler equations can in principle give you the answer. But the problem with the Euler equation in those days is because they involve phi unknowns, and it was a major task to solve for such equation with phi unknowns. So there is a simplification in this equation is called potential equation, which has one unknown. And people thought, we want to fly efficiently so that entropy is not a problem. So that's why the choice is, let us go for the potential equation, which is easier to solve, and practically also we don't want any entropy generations. So this potential equation is not capable of entropy generation. Is strictly speaking is not capable of taking care of the entropy generation, whereas Euler and Navier-Stokes equations are capable. So there was the results, initial results has revealed this fact. And then there is something called a Stockholm Olympics. German Mathematical Society started to dig into this, and they arranged the conferences, and these conferences pointed toward the problem, and this problem is due to comparison of outcomes of the various researchers which use the potential solver and the Euler solver. So you see here, on the left hand side, the two graphs are the solutions of the potential equations, and different researchers have a different graph. This is the graph of the CL over the wing. So obviously there is something wrong with the potential equation, and the rightmost graph is the Euler equation, and this Euler equation is comparatively better. So now there is a clear-cut hint that we may not use potential equation. So from 1970s onwards, 1980 onwards, it was not discarded because people still use this, but then there is a trend towards development of the Euler equations and no development in the potential solver. So the same graph can be seen here at the scatter here. You see on the left hand side, there is a CD drag coefficient, and the right hand side, there is a lift coefficient. You see the drag with the Euler equation, which is a yellow star here, the scatter is very, very less. Scatter is the result obtained with the different researchers. So there is a consensus of opinion for those researchers who are using the Euler equations. So now we'll see what is other crucial aspect with this Euler equations here now. It is shock. In this figure, what you see is the shock over the wing. This black line is a shock. Now to hold this shock in a proper position, there is a balance of the delicate forces. Had there been a wall, then perhaps this shock would stay there because of the wall. But here there is no wall, and shock should be positioned correctly. And this correct position can only be possible if you include everything in your equations. So Euler equations does not correctly balance these forces. There are boundary layer effects, there are pressure forces, there are this all wake, form and drag. So these are all the delicate forces. So there is this problem. So that means you need to do more than something which is Euler. But nevertheless, now here, even if our CFD is inaccurate, so we are going towards accuracy and we are solving towards no, but even inaccurate CFD is very, very useful. How can it be useful? Because it gives us the detailed visualization, whether we want or not, because all the data are available, so we know. And even if there is an inaccuracy, it points towards proper trend by changing, and the pattern can be seen, the trends can be seen. So we at least we can hint into we march in the proper direction. So also, because you are doing it on the computer, you can be courageous and do various ideas. You can implement various ideas as opposed to doing experiments wherein the people would come to know if there is a stupidest idea. Then there is, in CFD calculation, even if you do something, nobody will know except you. There is a joke over here at this stage. The calculations, the experimental calculations, the entire world will believe, but except the experimentalist. Whereas in CFD, nobody will believe except the one who is doing this calculation. So that is a joke. But nevertheless, now there is a this CFD, which experiment cannot do, this numerical experiments, and this is apparent now. And we will see that for certain cases of vortex, wherein no experiment can give you the result. So now in this historical perspective, we are here in the 1975, around 1975. So you see how we are marching here. and what caused to develop this CFD. So we have seen few factors important for the development of this. Now, now there is a rigorous mathematics that follows. So far, we only were discussing about the finite difference, whereas finite volume is a physical in nature. It accounts for what is flowing. Let us say in this figure, what is shown is the flow. The flow can be of the fluid or can be of the information, which is not tangible. For example, waves. The waves which are very delicate. So this finite volume approach accounts for capturing what is flowing at a given phase. And this can be captured using the integral approach and not the differential approach. It in fact works for even if your domain has a shock waves, even if your domain has viscosities. So this was realized, and then slowly people diverted towards finite volume and left the finite difference. So this is, and this finite volume looked like this. Around this airfoil, we need a small volumes here. Now there is a clustering near the boundary layer is because of the experience that there is something various length scale and time scale phenomena goes on in the boundary layer. So we need more accuracy, more grid points are clustered. It depends upon who is solving and who is looking for what. So this is now the generation of the grid. So one of the major problem is also how to generate grid, which is useful for a finite volume method. Now, generally, how do we account for the error in the CFD is this formula, where C is a constant, depends upon what kind of method you are using. H is the grid spacing, the volume that we have seen, the small volume, and the gradient. We have seen what are the gradients. These are the gradients in the equation. So this is the pth order derivative. So higher the accuracy, better is the result. But the problem with the higher order accuracy is you need a more number of points. So there has to be balance between. Also, as you can see here, if your P is higher, there is a balance between H and P that is explained here. So I will not go into those. But this is a very simple formula, and it is useful in order to see what is going on. Now this guy is Godunov. He wrote a paper in 1959, wherein his idea, let us say we go for P and P greater than 1, which is what we want. We want higher accuracy, higher order accuracy. And then he well ahead, very in 1959, this was not, people were not aware of all this, because he published in a Russian journal. Nowadays it is known as Godunov methods, wherein he says that there are spurious oscillations if there is a higher order accuracy. Where are these oscillations? These are the oscillations near the shock wave, wherever there is the highest gradient, wherever there is a complex physics in the domain, you are ought to have these oscillations. And he has proven it mathematically using the Fourier series. So these are called as Gibbs oscillations. So this was the very well known result then. So you cannot go for a higher order accuracy. So what we should do? So these are all the discussions in the world of the CFD, whether we should go for a smaller H or a higher P, or where to balance, how to balance. This is Professor Bram van Leer. He showed that you can have higher order accuracies even if you have complicated physics, and he showed it in a 5-part paper, which is which is well known. So Professor Van Leer is very well known for how to get along with the higher order accuracy without having any oscillations and with a true algorithm, which is stable algorithm. So we'll not go into those aspects here, but essential idea of the Goodenow is uh, to take care of the information, as simple as that. So information can be from the left hand side or can be right hand side. So according to Goodenow, your numerical discretization should only the stencil that I have shown you, the stencil should account for the information wherein the information is the physical information. So your stencil should not have any point where there is no point of information. So that is what the idea of the Goodenow method. And it is very, very stable and gives very accurate results. So there are two thoughts of opinion, wherein there is a linearization and which is Van Leer method, and there is another which is Goodenow method. I personally like Goodenow's method. I have been implementing his methods along with some hybridization as and when as required by the physics there. Now to test all these schemes with proposed by all these people, there is a well-known problem in the CFD is the shock tube problem, wherein in this tube you are having a low pressure region and a high pressure region. So upon removing this diaphragm, the flow is set up, and in the below figure you see here is there is a shock wave which is traveling. There is a expansion fan. This green is the expansion fan, and if your scheme can capture this, then you are into the game. So that is a well-known shock tube problem. It was tough in those days, but nowadays it is an entry-level problem. So if you cannot solve if your code cannot solve, you cannot do CFD. So you see these are the results with the different methods, and the first figure is the Goodenow method. So it is very accurate in terms of capturing the physics and the stability of the algorithm. Where are others you can see these oscillations. These oscillations means it will blow. It may blow. Either if there are oscillation, other results you can see either they are oscillating or they are very diffusive. You never know where is the shock exactly. So that's why Goodenow schemes are conservative, and so these are the results with the different methods. Different people have proposed different method for this Euler equations. Now there is up till now we have seen that Euler equations are solvable, but they are very tough. But this is Anthony Jameson, who was in the Princeton then. It's his paper wherein he showed that it is fast. There is a faster way of dealing with this Euler equations, wherein he employed a Runge-Kutta method for a finite volume scheme. So this is a very good paper, and it changed the shape of the CFD. So wherein he suggested you can do computations not sequentially, but parallelly also, not the MPI or the parallel computing part, but Runge-Kutta method allows for all those computations. So this is the one of the paper which nowadays also this Runge-Kutta method we use even today. So this is so we are getting closer to what is today, what is happening today in the. But even we are not closer to what we see today, the colorful pictures of the CFD. But we are close to the accuracy here. So you see here, this is nowadays there is a consensus in this figure. You see the CL value, and this CL value is same for all the researchers now. And on the right hand side, what you see is the faster convergence. So this is a residual which converges faster. So we are okay with this. So this is where we are climbing our ladder here. In the 1990s, this we have no we have hit the wall there. We are in the by the 1990s and 2000. So today we are marching towards exascale computing, wherein we need parallel computers. We'll see those things as we go. So now we have in 1990s we have this correct equations and correct way of solving and accurate prediction here. So what do we do now? So the tension was after 1990s whether we can do is there a possibility that we can accelerate our uh, uh, algorithm, or how do we better visualize this result? Because we'll see that these results CFD dump various files which are data files, and you have to process them again. This is called as post processing. This automating of the mesh. Why? Because higher the mesh, higher the time. So better to have automated mesh wherein you wherever you require mesh, you just have a clustering of that mesh, and wherever you don't require, you. So this I will not discuss. This is a multi-grid approach. We will go. This is a multi-grid approach wherein you accelerate. This is a coarse mesh, and you communicate between coarse and fine mesh there. That is how you accelerate. But it's not that easy. This is just conceptual. That the communication requires time here. Now another challenge. Now these days the challenge is faced by the geometry here. If the geometry is see in this figure you see the geometry is very complicated. Had it been a simple rectangle, you can discretize it. But how to discretize this? So people started in the right figure here. You see the domain decomposition. So now you multi-domain, you take a multi-domain and then you discretize it. So that is even that is not simpler in 3 dimension. But better is the unstructured grid. So if you have a triangles, then you don't need this multi-domain. And these triangles can have an algorithm of its own, which is called Delaunay triangle. So it discretizes your domain here. The problem with this unstructured grid is you need a data structure. And also you cannot, order of accuracy, you cannot have the order of accuracy simply had it been structured grid. So again there is, but nowadays second order accuracy with unstructured grid is very, very powerful because you can solve various problems which are not regular domain, and it gives the result, faster result. So whenever under pressure, your choice is this. And whenever you want to go for the accuracy 7th order accurate, 10th order accuracy, then you perhaps go for a structured grid. So as I said, output from the CFD codes were difficult to visualize what is the trend, and in those days this picture is in the very old days where it was not possible to to post processes within a day of whatever the code calculates. So there was obviously there was need for a graphical output. So here what you see is the left hand side is the experimental result with the Schlieren images, and this is the simulated images. So so this is what was expected out of the CFD data, and then people tried to there is also a way to process in today's world of parallel computing. We have something called as HDF and all those processing units which processes the data and give you the result as you can see, and quantitatively as well as qualitatively. There is a company in India which is doing very good here. As long as the visualizations is concerned, they do the 3D visualizations, and this is called a virtual reality where you can walk through this data. I think this is from the Mumbai. Now we will go and we'll see now what are the problems here with the mesh. Suppose we want the shock to capture. So then I need a more number of grid points over here, right? So how do we do that? If we keep increasing the number of grids, then perhaps that's not a good idea because it will take longer. So that's why I will cluster the grids in the region where there is a shock, and then I will. But then what are the problems here is this is the calculation, but I will skip this. I just want to show you the problem. And how to improve mesh is again the simple formula wherein you look for the gradient here. These are the gradients. You see for the gradients and you cluster the grids near the highest region of the gradient. This is a very troublesome problem again, wherein if you want to see where are the gradients and if you apply that algorithm of the gradient based approach, then you are in a trouble again. Why you are in trouble is because I'm being faster here. Why? Because then there is a drag due to the screen friction which is on the top of this airfoil, but your grid is not clustered here, so you miss that drag and you eventually may compute the wrong drag. So you have to be very, very careful in all those ideas of adapting the grids. So there is one of the ways in which this is circumvented is this something called as J. Uh, hmm, uh, you define the function and then this equation what you see is the sensitivity of this J with respect to the parameter, the state variable, energy, mass, uh, and these are the transpose. These are the transpose of this the state variable. So you can solve it, and this will overcome the problem with the adaptive mesh. So this has been there, and on top of that, there is a optimization, systematic optimization now from this. So I have not covered that part, but you see, this gives you the correct drag, which is the blue drag here. Whereas you just adapt the mesh for the gradient, then you end up with the wrong drag. Again, if you solve the Euler equations here, there are two patterns that you get here on the right hand side and on the left hand side. Right hand side suggests some flow reversal, and which one is right? So this is called as carbulence, and the CFD higher order accurate CFD gives this carbulence here, but experimentally carbulence is required sometimes to reduce the drag and heat transfer, and but this carbulence is due to doing something as the nose, extending the nose into the flow field. But this some of the higher order CFD codes gives the carbulence without all this. So another state of the art is turbulence. What is turbulence? I'll be, so this is what is the niche, the expertise in this field is. We'll see what. So these are the images that we will see from the parallel computer from the Japan. Japan is still the first in the supercomputing world, and of course then there is USA. So this is the result for an incompressible Navier-Stokes equation, not a compressible Navier-Stokes equation. So this is what the turbulence look like. So if you zoom in, this is what it is. If you still zoom in, this is what it is. Now the interesting question is, what are we looking at? These are the worms, but what are we looking at? So this is the vorticity, and so where from this vorticity has come into the domain. So this vorticity is from, now this is a technical of the physics here. This vorticity is from the boundary layer, and then because there is nothing to dissipate this vorticity, it will stay longer. So whatever you observed is correct. Now how to this is all simulated results, right? So and these are all numerical results. So this is what is the analytical model of this vortex, wherein you see there is a solid body rotation, So you have a vortex in the center and you rotate the whole, suppose there is the water in the bucket and you rotate the whole bucket, and that is called a solid body. So these are the circumferential velocity and these are the vorticity. So you see in the center vorticity is constant and then is readily decreasing. So these are the images. Now how do you calculate this? So these are the standard deviations, 4 standard deviations that you have plotted over here. So these are the techniques of the CFD only, and to investigate into the realm of turbulence, there is no way, no experiment can do so. So there is only one way today that we do dig into the turbulence is through the techniques of the CFD. So the problem today, as if we want to solve the turbulence and we want to understand the physics of the turbulence, then there is a limitations of the computers. So we need more power, parallel computing. So this is the team of the NASA who says that by 2030 we should be able to do the parallel computing. But it is not only about the architecture of the computers, but it says that you need improvement in the numerical algorithms also. So there is a big way to go. Even CFD is not finished yet. So where is the difficulty? This is a very great quote from Sir Horace Lamb here. He says that there are two phenomena that he wanted to investigate: quantum electrodynamics and turbulence. So he is not optimistic about the turbulence. So that is what that is what this phenomena which we are looking at is complicated. Now in this here we say that the length scale of the turbulence that is very atomic level or a micro level, but we are interested into the scales which are macro level, and at a macro level there are unlimited degrees of freedom. So now how to link all those things? These are the problems that we face today. I think I will stop here. Thank you very much for your patience.
Yeah, thank you, Dr. Kedar. Thank you for such wonderful talk. Now the session is open for question. Participants, do you have any question?
So friends, you can just raise your hand or you can put your question in the chat box. Either myself or Amrish sir will read out those questions. Or you can raise your hand so that you can unmute your microphone and then you can speak. Yeah, all the participants, you can put your question in a chat box or you can raise hand and then unmute your microphone and then you can speak if you have any questions or queries or any comments or any suggestions to make. Kedar sir, you may stop sharing your screen.
Okay.
Hello.
Yeah, please.
Sir, Yogesh here.
Please, Mr.
Yes, Yogesh.
Kedar sir, thank you very much for this talk.
Welcome, you are welcome.
Yes, and as I am from the background of computers, at your start of the discussion, you talked about Moore's law. So what I understand from the Moore's law that the price will actually reduced.
Correct.
But I read and it was a bit confusing. So will you please throw some light on that slide? That how the price is going to
price
be
is in fact reduced. So we see we are going towards the steeper the curve, the reduce the price, right? That was MIPS per dollar. So the value of the computer, this is usually started by the computer manufacturer, and IBM is one of them who initiated such kind of terminologies.
Yes, yes.
So wherein steeper the curve, you see MIPS per dollar, so per cost. So you see, you are sending, if you are going up above, that means you are having higher MIPS and the same cost, right? So
Oh,
that is what
yes,
it is.
yes. So
So
if
higher
you,
MIPS means, and MIPS, by the way, I am not from computer, but 100 MIPS and 120 MIPS from my physics point of view, sometimes 100 MIPS computer gives me the better result than the 120 MIPS. This has been observed. So I
yes, yes,
don't
yes.
know. So that's,
And that is another law. That is
yeah,
Amdahl's law.
yeah.
Yes, yes. So you are right in
So,
that.
and if I may ask you, Yogesh,
Yes, sir.
Moore's law is also about doubling the computing capacity.
Yes, sir. Definitely.
So that
Hmm.
is MIPS. So this is what I mean. MIPS is computer capacities. In terms of the computing is only MIPS, but there are other certainly other aspects which are not considered. So that is why this is a rough graph.
Yes,
Yes,
every
yes,
few
yes.
years,
Yeah,
the computing capacity doubles itself.
Mhm.
Yes.
And these few years are getting compressed with every
Compressed.
jump in technology. That's
Yes.
why the
So,
curve is of this shape.
True, true.
yeah. Thank you very much, sir, Kedar, sir. Thank you.
Thank you.
In Dr. Kedar, may I ask a question?
Sure, sir. Sure, sir.
Yeah. In India, you see many, like if you go to this National Aeronautics Lab in Bangalore,
Hmm.
and they have some wind tunnels which are there where they actually simulate real life problems of wind turbulence.
Hmm.
So they mathematically also,
Uh-huh.
it can be represented, isn't it?
Sure, sure. So there is obviously if you want to extract the data out of those wind tunnel, you require the background of this theory, because
Hmm.
what to measure, how to measure, where is the inaccuracy, where can be the uncertainty. Without the prior background in the theory, this wind tunnel testing will cause enormous error.
Correct, correct.
So
That is why a lot of mathematical modeling also happens at the back.
at the back, true. And this they do only when you have certain results which are theoretical, and to validate those results you do
Hmm.
those uh, calculations, because
Hmm.
this now these days in the supersonic region,
Hmm.
testing with the wind tunnel is very, very expensive.
Hmm.
And whereas these calculations, theoretical calculations, are almost nil, I mean,
Right.
these days. So that's why you do the calculations, and then you validate with the experiments.
Hmm. Okay.
So for example, in this gas turbine wherein the stall is observed, so these are this rotating stall which fails the turbine. Gas turbine is the part of the aircraft engine,
Hmm.
wherein higher the speed, uh, there are certain phenomena because of the shock interaction, wherein you predict something with the theory, but to gain the confidence you have to go with this kind of testing.
Hmm. Hmm.
Yeah, so this is a
So,
cycle.
correct. Correct. And this could also help in looking at the heat that is generated around the vehicle,
Sure,
uh,
yeah.
isn't
Sure,
it?
sure.
So
Yes,
that
yes, yes.
could reduce disasters also.
Yes. So these equations have this potential for the heat into those inbuilt. So
Hmm.
wherever there is there are these are Reynolds number, Prandtl number, Peclet number, which you can see by the dimensional analysis. So wherever you see is correct. So wherever there is a heat dominated region, the equations will trigger those terms, and
Hmm.
then this can be also analyzed with the same equations.
Okay. Right. Thank you.
Thanks.
So, Dr. Kedar Pathak, On behalf of participants, I just want to ask one question: where the future lies, like learning this CFD software or coding this CFD, or learning this numerical methods and doing coding at your own?
See, these are
For the student, what is beneficial?
the individual tests, right? It is up to individual. Somebody who is wanting to apply and earn immediately, then he may prefer this software, wherein you press the buttons and you get the results. But strictly
Yes, sir.
speaking, as I said, and many of the researchers says that there is how to interpret the result is very, very important here. So use of software to certain extent is very good, but it cannot be, it should be restrained to certain limit. Beyond that, if you use for research purposes, because that is why in the journals, well-known journals, they will not allow you to use the results of the commercial software.
Okay.
So you have to have your own in-house technology, higher order technology. So that's the way it is.
Thank you. Any questions from the participants?
Amrish,
Okay. Okay. Yes, sir.
just let me read out a comment given by one of the participants.
Okay.
Have the knowledge of CFD in designing food processing equipment like heat exchangers? If yes, how?
Can you repeat the question?
Sure.
Uh-huh.
Apply the knowledge of CFD in designing food processing equipments like heat exchangers? If yes, how?
Obviously, the answer is yes. Heat exchanger, you see, is based on the fundamentals of the flow. Without the convection, you cannot have right heat exchange. I mean, heat exchangers, the convection is the dominated phenomena, and this convection is the left-hand side of this Navier's equations. So you have to account for the flow feature, and then on the right-hand side, you have the Q term there. So this is how you apply this whole equations there, and depending upon what you are looking at, you will immediately come to know. Depending upon the boundary conditions, the inlet conditions, the outlet conditions, this flow will, these equations will predict the solutions in terms of what you are looking at. It depends upon what exactly is your application. I mean, in terms of the quantifying parameters. So, for example, there are various heat exchangers ranging from high range of Reynolds number to low range of Reynolds number to high mean temperature, LMTD to LMTD. So these are all people do every now and then with the equations of the CFD.
Yeah, Mr. Mayank Singh, if you want to further comment on that, you can unmute your microphone and speak to the Dr. Kedar directly. Mr. Mayank Singh.
Hello.
Yes.
Yeah. Good evening, sir.
Good evening.
Yes, sir. Sir, actually, sir, I just want to know that means if we can apply the knowledge of this CFD in the pasteurizer, as in pasteurizer, the hot fluid used to flow where we used to get the heat transfer. I basically don't have much knowledge about this CFD. While I was pursuing my master's, I heard this term through my guide. She was from the IIT. Then from there on, it was in my mind. So I just found that the webinar is going on the CFD. So I just watch it. So I just want to know. I just want to know more about it. So that is why I asked the question. So can you please suggest any books related to it, sir?
There are many books. One of them is Tunnel and Fletcher.
Okay.
Tunnel, Fletcher, and Anderson. There are three authors: Dale Anderson, Fletcher, Tunnel. So this is a very good book, which covers all the aspects for a beginner.
Okay. Thank you, sir. Thank you very much, sir.
Yeah.
Where are you from, Mr. Mayank?
Yes, sir. Sir, I did my doctorate from a National Dairy Research Institute, Karnal. Basically, I am from the food background, dairy engineering, and currently I am working in Vadodara in Parul University as assistant professor, sir.
Nice. Okay.
In fact, one of my PhD student had worked on the designing of this heat exchanger tube. We took only one of the tube, made it two-dimensional, and see how best we can enhance the heat. And he went to this dairy, Mehsana, Dudhsagar.
Yes.
Yeah. So he applied, and we have seen that experimental data as well as the theoretical data.
Yes, I worked there as a process engineer for some time while
Yeah.
I was working in the GIA. But actually, the basic concept related to the heat exchange and dry designing, unfortunately, they do not take place in India. They used to come from outside. Means here the assembling only occurs. So that is why. So I just wanted to know all the things. So
Yeah.
thank you, sir. Thank you for sharing the information. Thank you a lot, sir.
Welcome.
Professor Mike,
Okay.
Done with the comments on the chat box.
are there some more comments?
No, sir, that was the last.
Okay, then I think Professor Michael might like to say a few words.
Yes, thank you so much, Provost Nile. Yes, this was a wonderful start to our webinar series. So yeah, thank you for everyone for coordinating this event. Certainly Provost Nile, Dr. Amrish, Dr. Dinesh, and our wonderful and extremely knowledgeable speaker, Dr. Kedar. Thank you so much for today's talk. And of course, those who attended, thank you for attending. And we look forward to seeing you at our future events. Again, several more of these coming and a long range collaboration to follow. So thank you so much. I want to thank you all for attending and wish you a wonderful evening and a wonderful weekend to come. Thank you.
Thank you so much. Thank you, Professor Michael.
Thank you.
It's been my pleasure. Yes, fascinating talk.
Thank you. I hope I have not bored you.
No, not at all. It sounded fascinating.
Uh,
And I had a similar